Hello.
Am I audible?
Yes, sir. Yes.
Yeah, so just I wanted to know, it is showing like the stream is being done on YouTube. Like, can I get the YouTube link?
Yes, sir. We will provide YouTube link.
Okay.
Harshita madam, we can start.
Harshita
Uh,
madam.
okay, sir. Good evening to one and all present here. With immense pleasure and sense of pride, I, Harshita Vishwakarma, welcome you all to the second day of ATAL, sponsored CSE online faculty development program on research application on machine learning and Internet of Things, organized by the Department of Computer Science and Engineering. Chameli Devi Group of Institutions, Indore. Once again, I extend my heartful welcome to eminent academicians, industry experts, and distinguished guests. To begin today's session, I would like to invite our first expert, Dr. Gaurinath Banda sir, Associate Professor, CSE, IIT Indore. And the topic for his technical session is Machine Learning Based Internet of Things in Industry 4.0 and Overview. Doctor Gaurinath Banda is an Associate Professor of Computer Science and Engineering at IIT Indore, specializing in autonomous cyber physical systems, embedded systems, and formal verification. He earned his PhD in computer science from Roskilde University, Denmark, and an MS in Metatronics from the University of Southern Denmark. His research spans CPS, IoT, WSN, model checking, static analysis, blockchain, AI, and intelligent transport systems. He has taught and designed advanced courses in operating systems, embedded systems, and cyber physical systems, and hold multiple patents in energy conservation and brain computer interface systems. A, a recipient of prestigious EU and Danish government fellowships, he has led major sponsored projects, developed the Hartex real-time kernel, and received national and international awards. Prior to IIT Indore, Sir has also worked at Samsung R&D India and the University of Southern Denmark and has served in leadership roles at IIT Indore, including JEE Advanced Chairmanship. Now, I would respectfully welcome Sir Dr. Gaurinath Banda Sir to please grace us with his expert lecture.
Yep. Thank you, Harshita. That was a very elaborate message. Am I audible clearly?
Yes, sir.
And
Yes, sir.
okay. Am I visible also? Can
No,
somebody
sir.
come?
Now visible, sir. Okay.
Okay. Am I visible?
Yes, sir. Yes, sir. Visible.
Okay, great. So we'll start the session. I mean, you have. Let me just open my slides and then I'll connect. I'm just setting. Hold on, because just fixing the presentation. Right. So let me come back. Yeah, I'm sharing my screen. Can somebody confirm if my screen is visible?
No, sir, not visible till now. Yes, sir, now visible, now visible.
Okay. Right. Manoj, can you confirm what are you reading on this?
Yes, sir. Machine learning based Internet of Things in Industry 4.0.
Okay, great. Yeah.
Okay.
So welcome all. So it's a kind of very elaborate title. So there is a spell mistake here.
Yeah,
So
yeah.
basically, we are looking to, we'll try to understand something on machine learning at the middle of the session today, and then we'll spend some time on understanding what is Internet of Things, and then we'll go ahead with Industry 4.0 related discussion. Because this is a very concocted title. I don't know how you created this title. This is a very involved title because we need to take one concept after the other, and then we'll connect and we'll spend most of the time in understanding this Industry 4.0 related discussion. Specifically, we'll go through the definitive introduction to these concepts, and then some use cases that enforce that there is a need for a combination of machine learning based systems into the domain of IoT, and then they get deployed into the manufacturing, that bringing us to the Industry 4.0. Then we'll take a look at because most of us are faculty, so we need to see what is the market size so that our students can make contributions in that area, and in the process get prosperous, right? So this is what we are going to do, and then we'll talk a little bit at the very end, time permitting, what are the research and development challenges that you have in the area. Right. So this is my email ID. At any point, if you want to get in touch with me, you can find me online on this link and also on Google. So just make note of this. Primarily, I head the IIT Indore Autonomous Cyber Physical Systems Lab, where we focus on these technologies as of now. Specifically, and I could not add one more slide in here. So I'm the Industry 4.0 assessor, certified assessor by TUVCIT, which is a very important certification when you are qualifying your existing processes to be migrated to Industry 4.0 compliance. So let's start to look at what makes such a buzz when we talk of Industry 4.0. Specifically, as we have seen in today's title, it is talking explicitly about Internet of Things, machine learning based Internet of Things for Industry 4.0. So, as part of artificial intelligence, this is where you are having your machine learning part. We'll briefly understand what sets machine learning apart from the traditional algorithmic approaches, right, or rule-based systems. Specifically, the challenges faced in the Industry 4.0 are how to discover value and in the process use it to implement Industry 4.0 solutions. Right, that is the first challenge, because most of the companies are archiving their data, hoping that someday there would be some magic happening, and then we'll do a lot of mining of value from this data. Simultaneously, whenever we talk of connected systems, we do always have one challenge or the other, primarily due to cyber security related vulnerabilities inherent in the hardware platform, operating system platform, middleware, or the application layer per se. The third challenge, that is why I'm spending time with you guys today, is how we can enrich the skill set and give the required skill to our students so that they can find employment and create innovation in the field of Industry 4.0. So just bear with me, because we need to understand the definition. That is very important whenever we talk of teaching any new concept. So I made this definition, which is very precise. So we'll read it together. Industry 4.0 is a fourth industrial revolution like concept that is happening in the field of manufacturing, and also not only manufacturing, even in the service sector also, which can be characterized as the industrial process. This revolution is happening because of deep integration of Internet of Things, artificial intelligence, and data analytics. Right? This is the basic manifestation of Industry 4.0 as an integration of IoT, ML based data analytics. Right? So, what is happening with Industry 4.0? It is enabling smart, autonomous, and interconnected production systems. Right? Not only production systems, even service systems, we can say, that optimize efficiency, flexibility, and innovation. And specifically, it increases, more productivity for given resources. Right? That is basically we want, for a given set of resources, for the given set of investment, how we can optimize the production outcome. So let's see what is the historical timeline that has landed us in the current Industry 4.0. I mean, the Industrial Revolution started way back in the 18th century, right? Then, we are in now 21st century. So basically, the Industrial Revolution in 1.0 was basically driven by steam, right? This is the steam engines, and then, basically steam powered industrial plants, and basically predominantly driven by water power. And then it is all mostly mechanization like gears and all that stuff. There was no much electrical and electronic systems involved. Then we transitioned to Industry 2.0, which was predominantly due to the concept of electricity and electrical motor and lighting that has resulted in 24-hour manufacturing schedules, right? So we were working in shifts, and that eventually led to mass production, right? A kind of mass production that used to run 24 hours a day and 7 days a week, and then full 365 days in a year, right? That is a mass production, non-terminating mass production. Then we eventually witnessed a wave of Industry 3.0 in a silent format, primarily due to robotics, automation, and this is where you are seeing electronics driven automation and programming driven automation, and that's where you are seeing IT systems. Now we are in the 21st century, and then we are looking to the wave of Industry 4.0, which has given rise to the concept of smart factory, predominantly through IoT and AI and big data. Right? So this is how we are here as of today, as we are talking. We are witnessing Industry 4.0. What this Industry 4.0 specifically is doing is seamless fusion of cyber physical systems. We'll spend time in understanding what are cyber physical systems, and we also spend time in definitive understanding of IoT, and then we also understand what is AI that to enable autonomous real-time decision making in industrial ecosystems. Right. This is how the Industry 4.0 is manifested. Just this, to give you an illustration, I have taken this smart factory, which is a direct descendant due to applied industry 4.0. What we are seeing in here is, you can see there are workstations, right? You can see there is a conveyor belt that is moving in this direction, and there are automated workstations. So you can just say workstation 1, workstation 2, you can just say this is workstation 3 and workstation 4, and this is the supervisory control workstation, and you have got some mobile robot that is moving the things from one place to the other wherever it is required, right? So basically this is what we are having, and you can see for 5 workstations you only have 2 men, or two workforce is present in flesh, right? So this is what we are having. Specifically, what smart factory is all about is you have these workstations, right, and they'll be communicating among themselves. So what it means is, for example, if the workpiece is moving from here, then when it is about to be arrived, then the conveyor starts at an appropriate. It's not that conveyor is running all the time, so it saves electricity, and the precision is very well respected, and obviously removing the opportunity for manual error induction, right? So what you are looking in here is these machines do have either wired or wireless connectivity, maybe using standard wireless connectivity or proprietary connectivity on the machine floor, right? So everything is happening on real time, right? Depending on what events are happening at various machines, accordingly each machine reacts, right? So what you are looking in here is production lines can be altered. For example, this entire machine can be taken out, and you can move this machine in here if required. So basically production lines can be altered and customized in a matter of seconds, right? Machines are repaired. So for example, let me just undo some of the writing in here. So for instance, let's say this is the machine that is doing some welding operation, right? Imagine that it is having symptoms of failure, right? Then naturally the other machine would be communicated that it is down, and basically it can scale down its operation, and those things are communicated to the manager or shop floor manager, and in the process, whoever are to be given a kind of leave, they can be given, and in the process both energy and resources are optimized in terms of consumption. Then we go to what is the underlying fabric of Internet of Things, because you should remember that the slides are connected. We said that Industry 4.0 is making use of Internet of Things and making use of ML. So now we are zooming into what is there in the Internet of Things. That is what is the next slide telling about, right? So Internet of Things comprises of IoT devices. There is a connectivity between the devices. Each device is having its own sensors and or actuators. On the cloud and on the edge, we might be doing some analytics software execution. On the end application might be running both on the cloud as well as the IoT device. And since there is a connectivity between nodes, we do need to consider security issues, right? There's a duplication of this, so this is a security issue, right? So basically what is the advantage of using IoT in Industry 4.0 is that it directly establishes cooperation between machines through IP connectivity. In the process, it contributes to increased productivity. Whenever there is a problem, that problem is communicated through IP protocol onto the cloud, and predictive maintenance is done. It saves money in the process. And basically, whenever you are having some industry that needs to adhere to some compliance, it is very easy to establish compliance by virtue of the documentation. So this is the definition of Internet of Things which we gave from our lab. It is a system of interconnected devices equipped with sensors and actuators and or actuators, right? Communicating through lightweight protocols. It could be as heavy as IP protocol itself to enable seamless integration of the physical and digital worlds. Right. So this, for example, this is one reference architecture that we are looking in here. Uh, um, then we are having, for example, if you take a look at IoT nodes, for instance, right? So each IoT node in itself is a microcontroller entity that you are seeing in here. It has got it might be having a communication model, could be directly having an Ethernet based IP connectivity stack, or it is having a Wi-Fi connectivity, or it might be having its own Bluetooth or NFC connectivity, right? And it is obviously having a small microcontroller that is interfacing with both sensors and actuators, which is talking to the entity. Like for example, you can take this entity as a air conditioning system. So specifically what we are looking in here is, most of the time IoT devices are of this architecture internally, and most of these devices, like multiple devices, are connected as you are seeing in here. So for instance, what you are seeing in here is a overall IoT solution, and each of this node is, if you zoom in, you will be seeing this is your, and each node is of that kind, right? It might be having sensors, and each node, for example, what it is doing explicitly is that there is some common environment which is being sensed, and then there is a digital controller. Either it is an edge, then it is transmitting via cloud to the cloud, and then appropriate decisions are taken on the cloud. They get downloaded onto the digital controller, and they get imposed on the actuator, right? This is how the Internet of Things. We have developed one IoT protocol. We'll see that at the end. So you can see this is the Venn diagram, right? Recall from our school days, we usually have a Venn diagram to understand the concepts. So if you see this is a universe of systems, then what we have is, there is a Internet of Things and there's an Industry 4.0. When you have a intersection between this, we get to know something called as industrial IoT, right? This is what we are having in here. Then we go a little bit into the artificial intelligence, and we try to understand what schemes are going into the artificial intelligence. Predominantly these days what we are looking to is data set based artificial intelligence, is what comprises machine learning. Then a subset of machine learning is your deep learning, and primarily if your artificial intelligence is driving on top of vision information, naturally, if it is it might be making use of some computer vision rules. Then you might also be having robotics that is making use of artificial intelligence, which is part of your I 4.0. And if there is a kind of command being taken by humans, and the intelligence also generating some knowledge to be translated into speech for dissemination to the human in the environment, that is also possible. And in the process we have developed expert systems. Then partially, not all NLP is artificial intelligence. There are some NLPs which are not artificial intelligence, right? So there is a duplication of this. So again, let's try to understand, if you consider the system, the world of programming systems, this is your universe. Then this circle is talking about programmed systems, right? That means traditionally they are rule based, if then else control logic. And on the right hand side, what you are seeing in here is artificial intelligence based systems, this one, right? Artificial intelligence based systems kind of have sudden intersection, but not more, right? And what you're looking in this diagram is, what is the relationship between various entities comprising artificial intelligence, right? Machine learning is predominantly being explored these days in the research community. Then these days generative AI is making a lot of buzz. You have got artificial general intelligence, and then you have got a intersection of NLP and artificial intelligence. So again, remember that machine are, most of the time these days people are talking, when we see most of the presentations in AI, they talk of ML. But remember that AI is substantially larger than, sorry, is larger than ML, right? So basically, sorry. So it's very much larger than right. So basically, if I want to write a relation, right? So we need to do like that. So literally, what we are saying is ML is a subset of AI, right? So specifically, that's what we are talking. Then most of the time, the biggest challenges in AI is understanding whether what is the basis for their coming to a decision, proving that they are safe, and then we also need to establish that there is a fairness in the decision making. Another set of challenges is how to create data sets that have got the inbuilt pattern that we are going to discover, right? And then particularly bias free correct data sets for ML, right? So specifically, this is what we need to do. There are many opportunities in the area of artificial intelligence to make safe proofs for the AI and also developing synthetic data set frameworks. So, what is AI? Like, I just wanted to show you some definitive part. Like, let's go. So, you can pay attention to this definition in here. Um, Artificial intelligences are a collection of techniques to make computer programs that run on machines to perform tasks that typically require human level intelligence, right? Such as learning, problem solving, and understanding the domain. So specifically, this is what we want to understand in here. AI is not equal to ML. ML is a subset of AI. Particularly, ML, if you want to look to what is happening in ML through datasets, essentially datasets bring experience or human-like experience into onto the machine, right? That is what we are having. So on the other extreme is your classical algorithmic approach. Computation is done on an input to calculate the output, right? So we are writing algorithms explicitly through sequence of steps to converge to a specific output of just having the properties that we are interested in. Right? On the contrary, what we are looking to is artificial intelligence approach. Uh, you know, what is we need to encode experience, and then through the experience we indulge in inferring the output for a given set of inputs, right? So machine learning is one way to bring in experience as a data set. And for example, the models that we make in the machine learning are equal to cognitive processes, and model training is almost equal to learning in humans. Specifically for India, right? We need to be very much focusing on these technologies because these are the technologies that we as teachers should inculcate, pass on knowledge to the students because this is where a lot of opportunity exists, right? For example, Industry 4.0 is an application of digital transformation to industries, manufacturing, plus service sector, right? So basically, these days we hear a lot about digital transformation. We'll spend some time in understanding the basics of cyber physical systems because you should know it. And combination of these guys in here together with these guys, you make your industry 4.0 based on IoT plus machine learning. For instance, just look to the size of the market for IoT devices. The market that exists is approximately these many $1 billion, uh, targeted for year 2031. And in terms of numbers, as of year 2020, it is said most. I did not insert the references because there are many references that exist. And it is forecasted that during 2 years back, 29 billion instances of IoT devices were installed. What are the challenges? The biggest challenge in IoT research is how to tame heterogeneity. Heterogeneity at the hardware level, protocols, connectivity, middleware platforms, operating systems, etc. And again, whenever we have connectivity, you need to address cyber vulnerabilities inherent with each of these entities that we enumerated above. So opportunities for students to develop tools, IoT systems, middleware, and then applications solving unforeseen problems across various verticals. So, whenever we talk of a new concept, for example, Industry 4.0, as we said, there is always a need for reference architecture, right? So, unless and until you have a reference architecture, you cannot adapt I 4.0 for the existing industries, right? To make this possible, like a structured framework is required to align technologies, processes, and business models, right? The most widely accepted reference architecture is RAMI 4.0, right? This is coming out from Germany, where this RAMI architecture is proposed. So for instance, this is one reference that I have taken. So specifically, why we need to have reference architecture is that we need to define. There is a lot of communication happening within the I 4.0 and between I 4.0 and other guys. So we need to have specific structures defining the communication, and we need to have a development of a common language with its own science, alphabet, vocabulary, syntax, grammar, semantics, pragmatics, and culture. Right. So we'll not be spending much time on it because we only have 1.5 hours. So we'll just see an overview of this based on a reference material that I found from Rami people. Right. So the reason, in order to overcome that, they have proposed RAMI, which is standing for Reference Architecture Model for Industry. This is German language, so Industry 4.0. Basically, let me go forward and we'll come back. Okay, I'll just go ahead. Right. So basically, I will show in the next slide. So RAMI is a three-dimensional map showing how to approach the issue of Industry 4.0 in a structured manner. RAMI ensures that all participants involved or stakeholders involved in discussions understand each other, and so that we do not run the risk of again introducing manual error. Right. So let me change the slides here because I want to tell something else. So let's first spend time on understanding. Okay, let me just go here. If you have any questions, please, moderator, you can let me know. Then I can take the questions.
Surely, sir.
Right. So let me give you an orientation of what we have done in the lab in terms of. So we have worked in the lab specifically on a protocol called Open 1IoT Protocol, which makes it possible to onboard any IoT device if it is compliant to our protocol. It is the IoT device used for IoT device management. Specifically, we developed the protocol along with its grammar and defining the behavior of sensor actuator together with a IoT device control app, which is an Android app. Right. So let me go forward. Specifically, this protocol that we have developed is can be adapted by original equipment manufacturers who are the guys producing IoT devices. That lets their devices to be forward compatible without the need for any protocol updates. Right. Operational, it provides an operational framework, minimum criteria for a device to be qualified as an IoT device, and we have developed a language that lets to declare the capabilities of a given IoT device as a manifest file. And this protocol also made it possible to develop a IoT device control app, right? The ICS stands for IoT device control app. This protocol is the application layer protocol. So if you consider the stack in here, so what you have is basically you have your hardware, you have your operating system, and this is where our one IoT gets installed, right? So this is that's why we are calling it as an application layer protocol. It has got a discovery phase. We'll not spend time on it because it takes longer to tell about it. We have got probing phase, invoke phase, and configuration, right? So basically, devices advertise themselves. Like for example, if you see in here, this is where your mobile phone is installed with a user agent, right? And you will be having our app through which devices can be controlled. So what happens specifically is that once you power on this device, it reports its IP address onto the vendor portal. Users log in with the user credentials. They claim ownership of the device, and once the ownership has been established, the manifest file is directly communicated, transferred from the device to the user agent on the mobile phone, which is a ICA, and that makes it possible to use a single ICA to create the user interfaces for multiple devices post authentication. And each of these device is compliant with this case. But specifically, what we are looking in here is what is happening in here. Like step one, it is advertising itself. As soon as you power it on the advertising, it sends its IP address, right, and details to the vendor portal. This is your vendor portal in here, which there is like one-time login credentials that are provided on the with the device when the device is purchased by a user owner. So literally, uh, once this IP address is reported in here because of the one-time login credentials, the owners can install our app, and then our app directly communicates with the vendor portal, right? And then once it is done, ownership relation is formed between this device and this owner. After authentication, what happens is this manifest file is sent to the user agent, which is our ICA, and then appropriately a user interface is generated on the Android phone. Once a user interface is generated, depending on the capabilities of the device, a user can invoke those operations. Right, this is the, in order to write a manifest file on the device, you need to have a text, right? So for that, we have defined this grammar in here. So a manifest file can be written using this grammar. And once the grammar is written, once the manifest file gets verified by our algorithm that we have developed, I'll not spend time in here. So basically, we have got a verifier to ensure that manifest is indeed correct. This is how the parsing happens, and once successful parsing is done, then errors are not reported. Then it's clear to generate the UI on the user agent. Right. So we'll go ahead. So basically, we have done the experimental setup using our app on the Android phone, running on a Ubuntu PC. I mean, Cloud Node is web server is running on Ubuntu PC, and then we have got the thing which has been implemented as a Raspberry Pi based device, right? So let's go back to, so once because why I've told you about this protocol is, this is how you get the connectivity between the devices. This is the user agent or ICA app snapshot of claiming control on it. For example, we have just given a most illustrative one for air conditioner. So once the manifest file is transmitted onto the user agent after authentication in here, you can see the user interface is generated on the fly, and users can touch and then for example here the temperature was 16. They have done a plus plus operation in here. Then you can increase in terms of 0.5 degrees. So you can see here, this is how we have simulated the connectivity from the user agent to the thing node. So these are all experiments, and we compared how we are doing. Our protocol has an advantage in terms of against various existing protocols. Right. So we'll come back to the slides because I wanted to, after doing this IoT, I want to spend time on RAMI part. So before doing that, let me go to the cyber physical systems part. Any questions, guys? Please stop me if you have any questions, then we can talk. मनोज आप वो चैट बॉक्स में देख लीजिए, अगर कुछ क्वेश्चन है तो मुझे बोल दीजिएगा.
Sure, sir.
So, basically, whenever we talk of Industry 4.0, the concept that we always talk is IoT, cyber physical systems, ML or AI, cyber security, right? So these things we always talk. Of course, analytics is also one thing which is so-called entailed by your ML, right? So let's understand what are cyber physical systems, right? For example, a simple cyber physical system, when you remove networking, right? Like for example, if there is no networking, then it becomes an embedded system. But if it is having networking and the coordination between multiple nodes, then we have a cyber physical. For example, this is a network that qualifies to be called as cyber physical system, where each of this might be having a sensor or actuator together with some processing power. Definitely, they should be having connectivity either by Wi-Fi or wired or proprietary. Right. So basically, when your transmission and reception in a CPS happens through IP protocols, they qualify to be called as an IoT. Otherwise, they qualify to be called as a wireless sensor network if they use some proprietary mesh kind of communication. Right? Cyber physical systems, why are they called so? If you see, cyber physical system is a kind of phrase of two words belonging to different worlds. Like cyber world is what is present in the form of a digital controller, and physical world is present in terms of continuous dynamics, right? Like temperature varying continuously with respect to time, and both these worlds are connected by sensors picking the information from the plant to the controller, and actuators that take the controls from the controller and impose them on the plant. Specifically, systems involving cyber physical systems have a very tight integration between physical and plus networking. Right. So basically, this is the big picture of what are cyber physical systems, and they obviously appear in almost all Industry 4.0 manifestations. Right? So there are cyber physical systems everywhere, including manufacturing, workflows. Right. So this is a simple introduction to cyber physical systems. Right. So let's come back. Manoj, how it happened? Should we stop for a few minutes so that we can talk to the guys? If you have any questions, or should we continue?
Sir, I have posted participant can raise their questions in the chat box, but right now there is no question in the chat box.
Okay, great.
So yeah.
Okay, so we'll come back. So then we spend some time on so-called as let me come back to this slide again. Right. Whenever we talk of, as I said, whenever we talk of Industry 4.0 nodes, basically there is a hardware fabric, right, which includes some kind of CPU, some kind of sensor, some kind of actuators, and some connectivity, right? And on top of it, most of them have a kind of middleware or an OS, right? And on top of it, there will be your i4.0 app software. Right? This is how it looks like. So most of the Industry 4.0 have very strict real-time requirements. They mostly are hard real-time. That means if some event has happened within certain deadline, this needs to be sent out of the node, and and the other node should send its response, right? So basically, in our lab, we have developed a real-time kernel that sits on top of the hardware, which can be used in the industry 4.0, right? Basically, we developed a modular, these days there is a programming language called Rust. We developed a modular real-time kernel in the language of Rust, which is boasting the features of memory safety, constant time scheduling, and we also implemented it for dual core systems. We made it for STM32 and NXP dual core microcontrollers. Right. Most of the time, in Industry 4.2 cases, we only use microcontrollers, not CPU. I don't want to use not microprocessors, right? So basically, we use microcontrollers. So we'll spend some time in understanding this architecture of the real-time operating systems used in Industry 4.0, right? So basically, this is what we need. So I'll just little bit increase the pace because we almost are coming close to like 1 hour. So let me just increase the pace. Right? So most of the time, operating system, if you consider this is the operating system, at the core of the operating system is your kernel, right? Recall a Linux kernel, like for example, if you have a Ubuntu operating system distribution, for instance, it has got modules, additional modules plus Linux kernel, right? So in the same sense, we don't need for most of the Industry 4.0 applications, we need a middleware or a very thin kernel so that it doesn't introduce any non-determinism. So we developed such a kernel in the language of Rust. So basically, these Industry 4.0 qualify to be categorized as CPIoT systems, cyber physical IoT systems, which demand timing guarantees in terms of responsiveness, and they need absolute determinism, and they establish some kind, they need to be having assuring you some safety, right? So specifically, there are existing kernels through which we made a survey, and they were mostly prone to various problems here. So this work, what we have done is we developed the hard real-time kernel in the language of Rust, which is based on the Boolean vector scheduling, constant time, and then we have made context-aware communication. It works for both single core and dual core, and we made use of stack-based priority ceiling protocol and multiprocessor resource sharing protocol. This is for the single core. This is for the dual core. So, most of the real-time kernels have certain issues, like we'll go ahead, we'll come back to it if you have any questions. So let's see what exactly is that. Most of us already have taught operating systems course, so we talk about a ready queue all the time. I mean, just like in a computer, even in Industry 4.0 nodes, also we have limited number of tasks which the microcontroller or processor needs to juggle between. So we can assume that this is a ready queue, for example. So if you consider this ready queue, what happens is, most of the time we need to identify the highest priority process, right? So for example, if I want to use queue, what happens is it is having a kind of order of n complexity. So it is having fluctuating best case, worst case, and average case complexity. So what it means is there is some kind of latency associated with the queue data structures, right? In order to avoid such latency, we have encoded the queue as a Boolean vector, which brings in constant time performance of our schedule. Right? This is how we have organized our Boolean vector. Right? Let's go ahead, and this is the overall kernel architecture that we have developed. So basically, these are the tasks that are being executed on the I 4.0 node, right? and the external events are being reported by the external interrupts through appropriate sensors. So basically, these are where the sensors are there, and basically this hardware adaptation layer also emits actuation outputs, right? And we, in order to do this execution of these tasks need to communicate. So we have got a software bus that lets tasks to talk to each other, and then there are some resources, just like any computer, which needs to be utilized when the industry 4.0 node is delivering some functionality on the shop floor. So there is a resource manager protocol, and there is scheduler that is doing the dispatching of the tasks onto the CPU, and you have got a integrated event manager, right? So basically, you might be some
Excuse
events
me,
might be
sir. Sir, sorry to bother you. So
yeah,
one question is there in the chat box.
yeah,
Yeah, what are the most promising research area in ML-based IoT for industry?
yeah. So we'll come. So basically, industry 4.0, right? So that is what I said. We have got this Rami. We'll see. We'll just see in the last half an hour once I finish this part. But basically, if you talk about the middleware, like as I said, if you recall, if you see an industry 4.0 node from the computer science perspective, right? This is the stack of your I 4.0 node, right? This is industry 4.0 node. At the bottom is your microcontroller, right? And on top of is middleware or OS, and then you have having your apps, right? Basically, to answer the question, the most promising areas from the CSC perspective is you work on different communication protocols, different schedulers in different languages that bring in a lot of determinism and lot of, for example, you can also develop a range of apps. Just like your Android apps, you can develop some apps for a range of manufacturing industry domains, right? Does that make sense, Manoj?
Yes, sir. Yes, sir.
So that's what we are doing. We have focused on developing a real-time kernel for this. So this is the proposed kernel architecture. We made it open source. You can access this entirely online. So we have got these modules in the kernel, which on demand you can turn on or turn off depending on your needs. So these are some algorithms that are enabling our kernel operation. This is a tasking model that we have used to implement our scheduler. And these are some data structures specifically that bring in a lot of efficiency that we have used. And then specifically, we have implemented Baker's protocol called a stack-based priority ceiling protocol from the JNS Liu's textbook. We have implemented that. And basically, this gives, this protocol, I mean, to cut the discussion short, this protocol guarantees deadlock freedom. There can be no deadlocks in our kernel. Right? Recall from the operating systems course, which you might have all taught. So deadlock is a big problem in operating systems. So would be a deadlock in Industry 4.0 node creates havoc. So this is, and also it is bounded priority inversion is there in the system. Right? So these are the two things which create a lot of problem, bringing in complete stall of the workflow. So this is a specific protocol that we have implemented. This is MRSP protocol. It's in short. This protocol makes to accomplish deterministic behavior even on dual core microcontroller. So this is basically what we did is since you need to have IP connectivity. And remember that if at all we use one of these, just let's go back. If you see, for example, these are n number of tasks. And for example, if you implement the IP connectivity as a task and giving it a high priority, the risk is that there might be a lot of latency associated with the inbound communication. So to avoid that, what we have done is, we have done this microcontroller would be having our real-time kernel, and it would be kind of having its own IP connectivity through ESP module. So we detached the microcontroller to do the connectivity part. ESP32 does 8266 does the connectivity, and one task is implemented as the highest priority, which would be interrupted after every communication has arrived, and then based on that, our high priority task establishes the communication related activity. What is the advantage of using Rust in Industry 4.40 applications is it guarantees memory safety, right? And compile time guarantees are always respected. And there is safe concurrency in threads if you are having multi-thread implemented. For example, most of the Industry 4.0 nodes obviously are implemented with STM family of microcontrollers and NXP if it is a multi-core is required. Our entire work has been done on this development platform of i7 processor with Rust compiler. Right, so these are some results. Let me not put it. So this is what we have compared with most of the existing kernels. In terms of language safety, we are doing good. Memory safety, hard real time, and all these things are going fine. So this is how we want to enter into this. This hardware adaptation layer is one area, like you have asked. Industry 4.0 requires hardware modules generation automatically given the specification of your target Industry 4.0 hardware, right? So remember that if you recall the diagram I have drawn, you are having your hardware here. So for example, let's say you are having our Harshark kernel is here. So for a vendor, in order to install our thing on the new hardware, we need to generate the hardware adaptation layer, which is specific to the underlying hardware. So that is what we have started our work towards it. Right. So any more questions then before we start the discussion on Rami, Manoj? I'm not able to see the chat window.
No, sir. Right now, no more question.
Okay, great. Great. So we'll go to the last part of the presentation. Let me go to. So these are the slides based on the original author. Like I will show you what is the original, who is the original author of this content in here. Let me just come here. So you can see this is the reference like that we have got. So minus, right? So this is reference number 6. And reference number 6 is at the very end. We have got. So the entire set of slides that I'm going to show later are an adaptation of the slides that you can download from here because it's a very heavy set of slides. So Dr. Carsten has very nicely summarized in that set of slides on which my slides are based on. Right. So let's continue on that. Are my slides visible?
Yes, sir.
Okay, good. So if you see in here, this is a very interesting because I'm focusing more on Industry 4.0 because you have put the title as Industry 4.0. What you are seeing in here is you can see this is a car manufacturing. I mean, specifically, they are manufacturing here chassis, right? You can see this is the chassis, minimal chassis that you have got, and there are some machining operations that are happening, and also welding operation, and you have got a, basically you can see this this robot might be moving, or that work pieces might be moving this side, and you are having the processing stations showing what is the state of affairs of the specific machines that you are seeing. It's a huge setup, and basically that is the reason we need a reference architecture model that lets us to develop scalable solutions. So basically whenever we talk of industry 4.0, industry IoT is a minimal fabric on which industry 4.0 works. Maybe the nodes are not talking on the IP protocol. Maybe there's a proprietary protocol between the workstations on the machine floor. But most of the time, for the ease of communication, IP based communication is preferred. Basically, most of the time you have got communicating elements, right? So basically, these are some guys in there, and we need to have language-based structure to specify various behaviors in here. And another thing that we obviously need is system integration, like multiple nodes talking to each other. And once you have got communication, you need to incorporate security protocols, and you also need to have framework so that we have a seamless understanding of the things underlying industry 4.0 stack. So let me just go ahead and we'll come back. Okay, so 1 second, let me just I have to try. Right, so specifically, if you see in here, is my screen visible, Manoj?
Yes, sir. Yes, sir. Visible.
What is it showing?
Sir, something is loading. Something is loading.
Okay, it's not working then. It's not working. So wait.
No, no, it's visible, sir.
Okay, but anyway, I'll just download it and do it. That's better. But what you're seeing on this, okay.
So one question is there. May I ask?
Yeah, please.
Yeah, what are the risk of cyber attacks in fully automated smart factories?
Yeah, the risk is very high. That is the reason. Like in our group, what we are looking is, the risk is very high because you should remember that. Let me just quickly tell you a small tutorial, right? So, new page after. So, are you seeing my screen, Manoj?
Yes, sir. Yes, sir. It is visible.
So basically, because you should remember that whenever we talk of cyber vulnerability, let's say this is I 4.0 node 1, and this is, let's say, some server, let's say cloud server, for example, right? And if proper authentication happens and there is no eavesdropping, right, the communication is seamless. There is no problem. But there are kind of spoofing, for example, and then you have got tampering, denial of service, right? And then there are four well-known categories of cyber vulnerabilities. Anything can manifest if, remember that, again, I'm using the word if because you have your hardware at the bottom, you have your kernel or OS or middleware here, and you are having your app here, right? So there should be a very good so-called cyber security related logging or mechanism that is implemented in your kernel or the operating system or the middleware. If that is in place, and we also need to have some kind of filtering in place of inbound communication, right? So basically, there are instances where the entire industry 4.0 machine floor machines might stall completely, right? So basically, this is very much the. So to answer his question, yes, these are our question. Yes, there is a high risk. And that's why people have got intermediary nodes that get the outside communication, and then they are delegated to the I4.0 nodes. Does that make sense, Manoj?
Yes, sir. Yes, sir.
Yeah, you let me know if there are any questions. I can
Yeah,
stop for you.
surely, surely, sir. I'm looking.
Right. So, there is a need for communication elements, language structure, system integration, and a clear understanding of all these dimensions. Right. So, if you see in here, this is the RAMI in pictorial format. Right. It has got three axes. Right. This is one axis. This is another axis. This is another axis. Right. So, this is how the three axes are there, and on this are there are layers, right? And then there are the hierarchy of devices, right? So this is your hierarchy, and on this direction is your life cycle value stream, like from the raw material further you are away, you are close to the deliverables, right? So that is what we are having. So basically RAMI is a three-dimensional map showing how to approach the issue of industry 4.0 in a structured manner, right? So basically it provides a comprehensive framework which makes it a systematic to understand industry 4.0 technologies. It is a service oriented architecture. That means almost all software interacting between each other as services, right? That means there is a very comprehensive integration exercise that needs to be carried out. Of course, through because of it is a service oriented architecture, we can always focus on each of the topic in here, right, and see what is its interface. Right? So that's how it works. Then obviously there's a standardized framework, right?
Sir, may I ask one question?
Yep.
Sir, predictive maintenance, in predictive maintenance, we are using machine learning with IoT. So, sir,
Yeah.
can you throw some light about predictive maintenance
Okay.
and how we can means explore further research in predictive maintenance?
Yeah. So basically, you should remember that. Let me add a page in here. Right. So you should remember that. Let me put. Let's assume that this blue box. Let's assume that this blue box that I'm drawing is your device, is your machine that you want to do predictive maintenance, for example. Right? This is, let me put, this is your machine M1, right? That you want to do predictive maintenance, right? So basically, you should remember that this machine might be having multiple modules, right? And you need to specifically know the failure models for each of this and how their failure would integratedly influence each other, right? So there is some concept called as, this PCM, Manoj, you heard of this?
Yeah, a principal component analysis.
Yes, yes.
Yeah, yeah,
Basically this is what we do, and then there is the FMEA, this is what we do, and then we do in combination of time series analysis, right? These things we do, and basically what it translates to, I will tell you, to the very good direction for research is, like, as of now we are dependent on the, whenever we talk of machine learning, right?
yeah,
What it requires, you need to have a very expressive and important data set, right?
yeah,
And what does that mean? Data set has captured some pattern, right?
yeah,
If imagine that the data set has not got that pattern, your machine learning model will always fail. Agreed?
yeah, yeah. Agreed, agreed, sir.
So now what we are doing in our lab is that we are working towards synthetic frameworks. So as of now, what is happening is why we are not able to have all kinds of patterns, because generating patterns on a real machine is time consuming, right? And there is no guarantee that the pattern would be witnessed ever by a machine. So for that reason, we are making synthetic frameworks to generate various data sets with minimum amount of time, within a minimum amount of time. Got it?
And sir, sometimes in case if sufficient data is not available, and if we are using data augmentation, the result may be misleading number of times, even if we are using deep learning models.
Yeah, it will be misleading because you don't know, right? Basically, the data is coming. It is like this, right? Augmentation. You should remember that. Let's see what is inside a data set, right? If you see a data set, generally, data set is a collection of points, right? Let's say you have got a collection of 100 points, right? And if I look to each data point pi is a tuple of observed values, right, together with annotation, right?
Yeah.
This is what is your data point specifically.
Okay.
So now you should remember that this is a m-dimensional vector, right?
Yeah.
So how many augmentations will you do? You, for example, imagine that m is 30, for example. So it could be that one vectorial value deflection might change that annotation altogether.
Yeah.
And imagine that this data type of this value is a real value, for instance,
Yeah.
right? And what is its neighborhood? It's infinite, right?
Okay.
If a feature is ranging over a real domain, it is what is its next value? Let's say I'll write one vector value is 1 point. What is the next value after 1.2? You have infinite points, right?
Infinite points. Yes, sir. Yes, sir.
So how will you do augmentation? Because augmentation is tightly tied to the annotation that you are already allocated to it. So
Okay.
basically, that is where by augmentation only you introduce bias, and bias is a very bad word in data sets.
Yes.
Once you introduce bias, your machine learning model would also exhibit bias, and it is as bad as a manual error.
Yeah.
Got it?
Yes, sir. Because sir, even in so many student project based on machine learning and deep learning, we are facing problem due to data set unavailability.
Yeah. So that is the thing. So the catch is this is where things are going ahead.
Yeah.
We made a lot of work in that
So
synthetic.
is there any sir a feasible solution how to handle this problem of lack of data set?
That is the only solution.
Yeah. Only solution.
Only solution.
Yeah.
Right? And we need to know the understanding of the process about which we are synthesizing,
Okay.
and we need to model the process like a kind of twin kind of process, and then we just split the data set, and then we annotate,
Thank you.
and that
Thank you so much.
creates synthetic data set. Is that clear, Manoj?
Yeah, yeah, sir. Clear. Thank you so much. Sir, one more question is there in the chat box.
Okay.
What are the latest research direction in IoT with AI and ML?
Yeah. So so I mean, this question is coming up again and again. Let
Yes,
me
yes, sir.
let me give you a computer science answer, because these things are. Let me just page after, right? So you should remember that all of our people in on this call are CSE, or what are these backgrounds?
Sir, most of the from CS background. Most of
Okay.
the participants from CS background.
So
Computer.
remember, all of you guys, like CSE is all about challenges that arise because of a CPU running some instruction, right? That's all. And this overall embodiment into which domain it is providing the service brings in domain specific challenges. right? So, most of the things, like for example, what you need to do is that you need to identify what is the domain problem that you are trying to solve with some automation, and you need to project it as an opportunity on the software system that you are developing, and then you need to work. So the question was, one of you have asked, what is the important research problem in AI plus IoT plus Industry 4.0? Was this the question, Manoj?
Yes, sir. Yes, sir.
Right. So, basically, there are no as such research problems on this joint equation in here. There are research problems everywhere on discrete basis, but you can figure out the dataset related curation problem specifically for mass production systems, for example. Or for instance, you can develop a specific IoT embodiment for a specific service sector. For example, you can provide an IoT based robotic solution or something like that. So remember all the time that I will just do it, and then we'll start that discussion again, Manoj,
Yes, sir. Yes, sir.
because this is coming up again and again, right? So you should remember that programming language, for instance, is used to implement a program or ML model. Agreed?
Okay.
And this program ML model would be running on top of an interpreter if it is Python, right? Or it would be compiled, right? And after compile, it runs on some OS plus hardware. An interpreter also runs on top of OS plus hardware. Agreed, Manoj? Any questions this far?
Sir. No, sir.
Right. Now, all the questions arise, right? So that's what I told in the beginning, right? So the programs, if you see the world of programs, they belong, if you see, this is a Venn diagram, right?
Yeah.
This is rule based systems. This is AI based systems. Okay. So in the AI based systems, you are only specifically talking about ML, right? And in the ML, maybe you are having deep learning or whatever. So there are challenges that arise because in the IoT, you have challenges in terms of heterogeneity, right? That should be handled at certain abstraction level, right? In terms of ML, you have challenges in terms of finding data sets, right? How many of you have generated how many of us have generated data sets? We are all using open source data sets, right?
Yes, sir.
How many of you have, how many of us have time to generate data sets?
No, sir. And it is really very difficult to
Yeah.
generate data sets.
So, and then when we go to Industry 4.0, we are talking of smart systems, right? Smart systems is all about, they give out sensed values, actuation values, and some intelligence, right? So each of them need to be mapped to this abstraction, right? Like, where did I put it? Okay. All of this translates to, where did I put it? Yeah. All of this translates, whatever I said there, you need to see this is the systems view. And, most of the time, like, that is what I'm trying to tell you, right? So in order to solve a specific Industry 4.0, first you need to identify what you want to solve, right? You cannot solve with one solution all problems. First you need to identify a problem, and that problem might obviously belong to the ML, or it might belong to the cybersecurity issue, or it might belong to the scalability. Based on that, you need to identify a solution and work towards the solution. Basically, first identify the problem that is outstanding, then you approach it through your research. Got it? And from time to time, most of the industries also publish white papers. So you need to read them. And there are some surveys also occasionally. You need to read surveys that are very new. so that we get the current insights. Right, Manoj?
Yes, sir. Yes, sir. Yes, sir.
Right. Good. So basically, because of Industry 4.0, we have flexible systems and machines with distributed functions and cross hierarchy interaction. Right. So remember that who are the stakeholders, they can talk through the information channels. Right. So again, remember that there was an access to, which is about the product life cycle. It comprises, development, production, sales, distribution. These are all the things, right? Basically, all the analytics come in this product life cycle management. Also, you can use the data sets with annotations to identify the intelligence of what is happening on your product life cycle for a given product or for a given production scheme for an item on your workflow. Right? So basically, we have got these three axes. One is your hierarchy, one is your product lifecycle axis, and architecture axis. So again, remember that the overall purpose of Industry 4.0 is makes things easy for the people, for corresponding people to manage. So it's you who decide where do you want to do the management, right? Like you can take a level, station level where the manual operator is, or you can just take a look at control device level, or you can go all the way to the final area where the device is processing the workpiece, right? So you also have a hierarchical organization flexible grouping. Right? So this is the Industry 4.0 itself. RAMI itself is taught over several weeks, so it is just an overview of it. So most of the components have got a communication part, digital part, and physical part, right? So I'll stop here and I'll take some questions if you have.
Sir,
Yes.
one question I have.
Yeah.
Sir, can you explore about some real life applications or problems where machine learning failed in IoT setting?
No, that is what I'm trying to tell you, right? So again, I'll tell you something. So you guys need to understand we are unnecessarily missing too many things. I'll write something, right? So basically, remember that there is a node. This is an IoT node. Let me write, right? IoT node is talking to other through the IP protocol. Agreed? And what is this IoT node doing? It is having its own sensor and it is having its own actuator and it is running its own program, right? So in that sense, this is more or less like a small computer, right? So specifically, problems don't arise because of IoT coming into picture, but specifically because of the domain into which the IoT has been deployed. It is specific to the domain of deployment. Not the problem won't arise because of IoT integration into the solution. Right. So basically, you should remember that if you see IoT is a distribution, it enables distributed system, right? So for example, let's say one machine is doing this activity. After it, at this time point Ti, it finishes this activity. Let me put this as machine one. Then a message is sent, right, for communication. Let me write to machine two, and machine two starts working here. So all kinds of problems arise because of the fact that there is this amount zero, Manoj? What is the duration of? Let me write this is Tj. So is Tj minus Ti equal to zero, Manoj?
Yes, sir.
It is not. And because of that, most of the things that arise in distribution systems are basically due to the transmission delays and jitter and bottlenecks and all that stuff. So it is not specific to, and that is where problems arise. But as we see, most of the reported works, this is the reason that is bringing in diversity that needs to be addressed. Otherwise, IoT nodes are small computers having resource constraints. In addition to this timing delays that bring in problems. Is it clear, Manoj?
Yes, sir. Yes, sir. Thank you so much.
So let's go to the last slide and we'll stop. Right. So basically, security, because whenever two nodes are talking, right? So it's a big deal, right? Whenever you have two nodes talking with each other, so you need to establish confidentiality, and the channel should also be confidential, no spoofing, no phishing, and all that stuff, right? So basically, that is a foundational requirement, security. On the day one when you start the research, it should be considered, and you need to have protection at each of the layers, and there needs to be a mechanism to establish trust in the developed and implemented RAMI model, and always innovation should happen to fix the patches wherever necessary, right? So security considerations must be integrated into every aspect of RAMI implementation, ensuring that the connected factory remains resilient, trustworthy, and capable. Right. So Manoj, can we stop here?
Yes, sir. We can wait for 5 minutes if there are some questions in the
Yep.
chat box.
Yep.
So, participant, please, you can raise your questions in the chat box. So, sir, I think there are no more questions.
Okay.
Harshita, madam?
Yes, sir.
Yeah, over to you.
Okay. Thank you so much, sir, for your profound words and guidance. Manoj, sir, is the next speaker in the meeting?
Ma'am, let me check.
Okay, sure, sir.
No, no, madam. Maybe might be joining within
Okay.
2-3 minutes.
So, should we wait then?
Yes, yes.
Okay, sir.
So, Harshita, ma'am, he has joined.
Okay, sir.
Yeah, Mr. Vishal Joshi has joined.
Okay, okay.
Yeah.
Now for the next session for today. Now I would like to invite Mr. Vishal Joshi, sir, IT consultant, Infobeams Indore. Sir, and the topic is IoT architecture and ecosystem, future trends and research direction. Mr. Vishal Joshi, sir, is an accomplished IT professional with over 16 years of experience in software development, project management, IT consulting, and more than 5 years in training, mentoring, and academic research. He has worked with top multinational firms like Accenture, Cape Gemini, and Wipro, delivering large scale technology solutions and driving digital initiatives. Currently serving as an IT consultant, he specializes in bringing business needs with technology, focusing on web application development using Microsoft technology, business intelligence and data analytics with Power BI and SQL BI tools, and process automation through the Microsoft Power Platform with a strong expertise in NET, SQL, Server, and Microsoft BI. He excels in building optimized data models, dashboards, and reports that enable data driven decision making. Sir's career aspiration is to advance further in web development, analytics, BI, and AI driven solutions while continuing to nurture future IT professionals. Now, I would now I would like to invite Sir to for his session. Mr. Vishal Joshi, sir, am I audible?
Yes, yes. Thank you, madam, for the introduction.
Okay, thank you, sir.
I'm just sharing my screen. Is my screen visible to all of you?
Yes, sir, visible.
Yeah. First of all, thank you and very good evening to all of you. And I'm grateful that such a large audience is just listening to me at the moment. And in the evening session, actually, because we are busy with our schedule. So here my topic is the architecture of IoT as well as the ecosystem and the future trends as well as the research direction. So this is the agenda of the session: introduction to the IoT, Internet of Things. Then what is Internet of Things? Internet of Things architecture, IoT ecosystem, and then IoT future trends and IoT research direction. So, as everybody aware of what is Internet of Things, wherein the various sensors are deployed, devices are deployed, and this is just a framework, although it has not been designed completely, but there are speculation which design model is better or which is not better. But actually, some of the organization has provided the framework as well as architecture regarding the same. So, in nutshell, if we can say that the what is IoT, then it is the collection of things, and things is just the collection of devices, and the devices are physical devices, just like the sensors as well as actuator that can exchange the information and can be managed with some of the other external system. So usually the IoT platform is consist of various things, but at the lowest level of the IoT system, we are having sensors and the actuators that reads the information and transfer the information to the upwards layer that we will see in the forthcoming slides. So in the IoT, we are having sensors and actuators. If we take the example of IoT sensor, then we can take the example as an air quality sensor connected to a central server where the user can see the current air quality reported by the sensor. And if we consider the example of the actuator, then air ventilation system connected to a central network that can be turned on or off by user by just sending a message to the physical device. Sensor provide information to the user about the environment, and on the other hand, user can perform actions over the other physical devices based on the information provided by the sensors. Another key point of the IoT system is the possibility of developing a smart application for a specific scenario. So if we consider the definition of the Internet of Things, then we describe the Internet of Things as a vast array of objects with sensing and acting devices that collect, analyze, and share the data across other objects, program, as well as platform. So as I already mentioned that the IoT system, the lowest level of IoT system is the sensor as well as the actuator that will pass the information, and that is gathered by the other layers of the IoT framework. And this layer in between process the information, transmit the information by using some of the protocols. If we see another definition of the IoT, the internet can be described as the communication network that connects individuals to information, while the Internet of Things is interconnected system of distinctly addressable physical items with various degrees of processing, sensing, actuation capabilities that shares the capability to interoperate and communicate through internet as their joint platform. So these are some of the basic definitions that has been referred by some of the research papers, and the references are mentioned here. So this is the basic diagram of IoT that we will see in the forthcoming slides. We will see each and every component of the architecture. There are so many standard technologies and the organization which has given the architecture of the IoT. But this architecture is most prevailing architecture, and this is referred, although I have already mentioned that there is no hard and fast framework provided by any of the organization as far as IoT architecture is concerned. But this is the layered architecture that is most prevailing one and used in most of the use cases scenarios. So it consists of the 4 layers. The first layer is the perception layer. The second layer is network layer. Then third layer is the processing layer, and the fourth layer is the application layer. So the downwards layer which interact with the environment, as we all know that IoT is just sensing something from the environment. It may be the humidity, temperature, pressure, etc. That are invisible entities that we cannot see, but these are sensed by the sensors, right? So the perception layer is the downward layer, and first we will see what are the characteristics of this layer, how this layer will work, and how it passes, what information actually it passes to the upward layer, which is the network layer, and then again the top layers and how they work. So actually perception layer is the downmost layer, and this is the foundation layer of any of the IoT system. It consists of endpoint devices, and it is referred to as a things. So the name IoT, Internet of Things, comes from the devices and the sensor, actuators, RFIDs, embedded devices. This can be referred as a things because they are the object and they are visible. So this layer acts as a mediator layer between the physical environment and the digital domain. Actually, as I already mentioned that the perception layer, the devices resides at the perception layer, uh, sends some of the information, environmental information, and then it passes to the upward layer, which is more towards the digital layer, like network layer or processing layer. And finally, the application layer, where we use the application and do some kind of analysis or anything. Then these devices may utilize wire or wireless connection, and the architecture allow flexibility in the choice and placement of its component. Another another work of the perception layer is to collect raw data from the physical environment, such as temperature, humidity, motion, and light. It also detects change in the environment and transmit data to the network layer. So as I already mentioned that it senses different environmental metrics or parameters, and then on the basis of sense, it passes the magnitude of those information or metrics to the upward layer, network layer. And most popular components of the perception layer are mentioned over on the slide: sensors, actuators, RFID, embedded devices, etc. So this is the perception layer. Now we will discuss on the network layer, how the network layer works and what are its components, how it interacts with the perception layer, as well as how it passes the information to the top layer, to the network layer. So the network layer facilitates data transfer across an IT system, ensuring seamless connectivity and communication among its components. It comprises data acquisition system that acquires the data and network or internet gateway. This data acquisition system plays a crucial role by aggregating and converting data, such as collecting information from sensors and transforming analog signals into digital formats. The network layer is responsible for transmitting this processed data to other devices, servers, as well as the smart system. It also supports the interaction between IoT devices and handles all data transmissions, whether wired one or wireless. It transfers data from the perception layer to processing or storage platforms. It also ensures the reliability of the communication done to the processing layer. And this layer also takes care of transmitting the data in the form of packets. A different kind of routing algorithm has been used on this layer. And so most of the, what I would say, most of the components are important components of the network layer are the routers, the communication protocols like IPv4, IPv6, etc. So this is all about the network layer. The next layer is the processing layer. So the processing layer is also very critical layer, what I would say, or whatever the analysis part done, the data that has been sensed by the perception layer is done on the processing layer itself. So this layer manages and analyzes the huge amount of data collected from the various IoT devices. It serves as a mediator between raw sensor data and actionable insights. This layer processes real-time data locally at the edge to minimize latency and ensure quick decision-making, while also handling data aggregation and analytics for long-term analysis in the cloud. It supports both centralized and distributed computing, and allowing for scalability and flexibility in processing demands. Machine learning algorithm, artificial intelligence, and big data analytics are often employed to extract valuable insight from the processed data. The layer ensures secure data handling, maintaining privacy and integrity of sensitive information. Moreover, it integrates with various systems and application facilitating seamless data exchange between IoT devices and enterprise platforms. So actually the job of the processing layer is to process the raw data into the meaningful information by applying some of the analytical algorithms. It also stores the data for the future references. So its job is to uh, convert the raw data or the information into the meaningful insights. And this layer also stores the data at its own for the future references or for future predictive analysis. Next layer is the application layer. So actually this layer is more towards the application that has been created, or the if in other terms I would say the software that has been created using executing the projects inside the IT organizations. So this is where the data has been processed. Means in this application layer, the data has been processed and utilized. So various kind of tools has been used to process the data at this layer, depending on the use cases. See, if we are more interested in doing the analysis, then the tools that has been used by this layer is just what I would say reporting tools, or the tools that will provide the functionality of creating the scorecards or dashboards or reports, etc. And this layer focus on providing uh, various services such as smart monitoring and predictive analysis, automation, real-time control, etc., depending on the use case. This layer also utilizes the process data from the lower layer to enable applications like smart homes, healthcare, monitoring, industrial automation, and logistic management. It integrates with the user interface, offering dashboards, APIs, and visualization that facilitate easy access to insights that is sensed from the environmental changes. It ensures seamless communication between IoT devices and external systems, enhancing efficiency and decision making. So this layer can be considered as a most user-friendly layer because the application that has been created from the inside data provided by the processing layer is consumed by the application layer, and then it will be uh, showcased to the user in various forms, as I mentioned, like uh, various applications. It can be a web application or reporting application or dashboard or any of the application that has been created by using the data that has been processed by the processing layer. So this is all about the architecture or layered architecture of it.
Vishal sir, sorry to bother you. One question is there in the chat box.
Yeah.
I'm just reading, listen carefully. If the received sensor data beyond the threshold range means is the ML algorithm send command to control the actuator, shall we control the actuators from dashboard manually?
Yes, we can control actuators.
Okay.
Hello.
Yes.
Yes, we can control the actuators
Okay.
if they passes the threshold.
Thank you.
These are the slides that I have already gone through. I was on the layered architecture diagram. So, and this is the actual IoT architecture diagram that is more towards the component of the IoT beside the layered architecture diagram. So we will discuss this. So as you can see, we have already discussed a few of the things in the layered architecture diagram. And these are the, what I would say, the various layers has been divided into the various component or block diagram, where it is sensor and actuators, which is consist of user IoT devices and third-party devices. Then communication network, which is having different protocols. Then IoT gateway. Then communication network. And the communication network comes twice over here. And then IoT platforms. And then finally the application that are more towards the user, like smart city, smart campus, smart community, and command center. So the first we will see the sensor and actuator. So sensors are hardware devices that measure physical parameter from the environment. Like I already mentioned, temperature, humidity, pressure, etc. are from other system. And actuators are hardware devices that carry out action based on the IoT request. Usually, these are the small devices with limited resource set. And in the simplest cases, the needed processing capabilities may be achieved using a small microcontroller without an operating system. When more complex capabilities are needed, a small operating system designed specifically for this kind of system, such as Tiny OS or Free RTO OS, etc. There exists a vast number of different types of sensors and actuators. These may have different sense, physical parameters, communication, and human interfaces. And in some cases, they may be also smart. So this component sensor and actuators are having two blocks, user IoT devices as well as the third-party services. User IoT devices are physical devices deployed by the user. Example that I mentioned, the temperature sensors. And third-party services are the services that are available as a part of, like I would say, REST API services that is known as representational state transfer services that has been deployed on the server and these services can be consumed by any of the firm who is subscribes for this service. So actually, this is the sensor and actuators that I explained. The second layer here in this IoT architecture diagram is communication network, which is more towards the bottom communication network layer, and that is close to the sensor and actuators or devices. And so to enable data exchange among sensors, actuators, and IoT platform and gateway, the communication network layer plays a vital role. The communication network must provide the physical link and network layer according to the open system interconnection model. The network layer is responsible for providing packet forwarding and routing. So as I already mentioned that this layer is also involved in converting the sense data into the digital data, what I would say like the digital packets that has been transferred over the network using the routing algorithms. And the protocol that has been used in this network layer are IPv4, and this is the very popular protocol. And it is having 32 bit of address and can have 2 to the power 32 addresses. And 2 to the power 24 addresses are more towards the private network or reserved for private network, out of 2 to the power 32 addresses. But this IPv4, because of large volume of the network and increasing demand of the servers, this IPv4 protocol has been decommissioned or going to decommission. And now the IPv6 is more popular. So this IPv6 is to the power this is sorry, it is 42 bits of protocol. So this is the slides that we are on actually, and this is the study, and it shows the various technology used in IoT for communication. Let's see the scope. Actually, the scope is proximity or personal area network, local area network, wide area network. Then the technology used like NFC, Bluetooth low energy thread, Zigbee, Z-Wave, Wi-Fi, etc. So these are the technology based on, most of the technologies are based on the various protocols, and the range has been observed as per the study of this reference. The range of proximity is less than or equals to 10 centimeter. If we come on the personal area network, then it is increased obviously, and the network topologies are defined at the scope level like star, mesh, tree, etc. And the data rate of this technology used in various scope. So wide area network is having 220 kbps per second, etc. as per the technology used for that scope. So actually, this is nothing but the role of network layer or communication network layer in the IoT. As per the study, this data is come out in one of the study. Now let me go to again IoT architecture diagram, wherein the IoT gateway. So this is the IoT gateway, and it is a device used for different communication network, data layer protocol, data formats. And in many cases, the IoT platform may lack direct support for some of this. To solve this problem, a middleware component called gateway or edge gateway may be introduced between the IoT platform and the IoT device. So this IoT gateway is used to bridge the gap between the different communication network. So it deals with the various protocol used by the different communication network, like other data formats, because as we know that the various communication network use the various data formats. So these IoT gateway are more towards the uniforming the different communication network and making the communication easier. Then finally, this is IoT platform, which is the layer just below the application layer. It consists of the three blocks: the application enablement, IoT platform management, and data storage and analytics. So the IoT platform is the central hub of the IoT system. enabling the connected sensors and actuators to be controlled and mentioned with the help of application. And it consists of the three application blocks. Our IoT platform consists of three application blocks: application enablement, IoT platform management, data storage, and analytics. So IoT platform management is provide several management functionalities related to the IoT platform itself. So the first functionality provided by the IoT platform is the creation and configuration of user account. It enables the creation of the account for different users that must interact with the IoT platform. So what I would say, as this is just like in the other applications, we are having network firewall. In the same way, this application enable IoT platform, or I would say the creation and configuration of user account. So IoT platform manages the users who interact with the system through the application. So this is, I would say, the security layer deployed or enforced in the IoT platform. Then the other part of this IoT platform management is the integration and management of devices. It allows the connection of devices to platform and configure the data to be retrieved or the possible action to be performed. Then it should be noted that and explained above the communication network component, different devices or gateway may be connected with different technologies to the IoT platform. Depending on this technology, the mean of connecting the devices may be different. Then again, the IoT platform management is having different role, and it is the data and system management. It allows for checking the status of the IoT platform. The system logs has been viewed and the backup copies has been done based on the user section over here. Then other part of the IoT platform management is the interface to the management and security layer of the IoT system. So these are the few of the functions that has been done by the IoT platform management. Then the second component of this IoT platform is data storage and analytics. This data storage and analytics perform the function of storing and accessing the received sensor data. And this data storage analytics also responsible for providing the functionalities of analyzing the data. So actually, whatever the insightful information has been yield from the data that has been provided by the communication layer to the processing layer, it has been processed and analyzed over here only. And the third block of the IoT platform is the application enablement. So this block provides the functionality for developing and deploying application for the IoT system. So actually, application enablement comes in the sense is where this the deployment of the application that has been created on the application layer is done. And finally, the topmost layer of the IoT architecture is the application layer. So as I already mentioned, this application layer is the software component that perform a specific task, rendering data captured by the sensor and or controlling the actuators. So it is application layer is what I already mentioned, that it is the more towards the user interface where the user interacts, and it is the user friendly layer. So the example of the functions done by the application layer is a GUI graph that displays the data from the sensor over the period, a GUI button that allows the user to turn on or off some devices, a rule that automatically turns on or off device based on the value provided by the another sensor. So these are the things that can be configured at the applications level, wherein we can control the sensors as well as the actuators. So this is the answer that one of the participants has of now asked, if some of the threshold has been passed uh, threshold or exceeded, or from the top range or from the bottom range. If it will pass, then definitely we can control the sensor as well as the actuators. Already we have covered. Just wait a moment. Yeah, this we have not covered actually. So as per the block diagram, we are having uh, two components that were missing in the layered architecture of IoT, the security as well as the management. If I will again show this, then this is across the all the layers, security as well as management. So they go parallelly in all the layers of the IoT architecture, and they are having different roles. Yeah, the security block is responsible for ensuring the confidentiality as well as the integrity and the availability. So as the name implies, security, it will provide the confidentiality as well as the integrity and the availability. So these are three parameters that comes under the security. Just like user authentication, user privacy, access control, monitoring and auditing of security events, and management of keys and certificates. So these are the various uh, classification in terms of the security. Some of them falls under the confidentiality, some of them falls under the integrity, and some of them falls under the availability. And the second, uh, uh, what I would say, the second thing or second block is management, apart from the security. So this management blocks allows for management task of IoT system that depends on other blocks. So it is managing the functions of all the components across all the layers. It may be the sensors, actuators, or communication network, or it may be the mm, gateway, or it may be the IoT platform, etc. So this is the actual diagram of the IoT reference model. So on the basis of uh, so Actually, it is more towards the network. What I would say is you can see on this uh, the various networks has been the role of the network. What I would say in this entity-based IoT reference model. So if we can see here in the diagram, the user network is there, then service network is there, then access network is there, and then proximity network is there. So actually, depending on the how the various entities are interacting in the IoT system, that this network has been used, or I would say uh, uh, applicable. If the IoT user is interacting with the network, then definitely the user network comes in the picture. If various subsystems are interacting with each other, then the service network comes in picture because they are providing the services to each other. Uh, if we are if the gateway is comes in the under the picture, then the access network will be there. And if the devices comes under the uh, picture, then the proximity network is there. So this is all about the entity-based IoT reference model, where the various networks comes in the picture based on the entities that are interacting with each other. It may be the user, or it may be the subsystem, or it may be the gateway, or the IoT devices, or any physical entities that are involved in the IoT system. And this is the another domain-based reference model. So it is more towards the domain, and it is having all the four network that has been used in the previous diagram, entity-based IoT reference model. So here we have divided the various components, or classified the various component based on the domain, like the user domain, where the users are involved. Then the subsystem domain is nothing but the operation and management domain, application and service domain, or resource access and interchange domain. So those subsystems are converted over here in the domains, and uh, IoT gateway and IoT devices are comes under the sensing and controlling domain, and the physical devices comes under the physical entity domain. So these are the various entities grouped together and form under the domain. And based on the domain, the IoT reference model has been depicted over here. Uh, Now, as a part of the ecosystem, these are the various things that we are discussing. So apart from the architecture, if we consider the ecosystem, then definitely it will involve some other things like the various computing models and different components that are part of the ecosystem. So we will discuss this one by one. Yeah, so IoT computing model, this model offers powerful services, unlimited storage, and computing capacity on demand. And these computing models connect smart devices to cloud, poses severe issues like connected devices create large volume of data, performance, security, bandwidth, and reliability concern. So To eliminate this kind of problem that arises in the cloud computing, we are having fog edge computing. This is the architecture. So what we mentioned over here is there were some limitation of the cloud computing. Uh, as there is large amount of data resides on the clouds. So definitely, if we will request some data that is residing on the cloud, it requires the network communication or the transfer of data from uh, cloud to the servers, personal servers, what I would say, when we are requesting something. So definitely it use the network where the various things comes in picture, like the performance of the network, the security of the data which is travel around the network, then the bandwidth issue may arises, and the reliability of the data is also comes in picture. So these are the few of the limitation of the cloud computing uh, in the IoT. So to eliminate this kind of issues, we are having fog computing. So this is the architecture diagram of the fog computing. Uh, so if I will take the example of a high-speed train embedded with hundreds of sensors controlling its journey, all the sensors reading can be sent to the cloud, and where the reading will be processed to detect abnormal condition and send command back to the train. So there are several problems in this scenario. The first problem is, as I already mentioned, the bandwidth to transport the sensor and actuator data to and from the cloud is expensive. So this is the real life example of the limitation of the cloud that I have already mentioned to all of you. So it may take hundreds or milliseconds to react to an abnormal sensor reading. And if the connection to the cloud is down or the cloud is overloaded, the control of the train is lost. So as an alternative scenario, this fog computing comes in picture here. So how this real-time scenario has been eliminated using the fog computing? Uh, we are having fog nodes inside the train, and those nodes can be connected to the sensor and actuator with the inexpensive local networking facilities. So instead of connecting to the cloud and transferring or taking the data of the train, we are having the sensors and actuators deployed on the train, and we can eliminate, we are having fog nodes inside the train itself, and that can detect that can detect if anything goes wrong inside the train. So this is the concept of fog computing, where we eliminate the cloud computing uh, drawbacks uh, by deploying fog computing itself uh, there inside the train. So the next is edge computing. So the architecture of modern IoT system should consist of four layers: a thin layer, an EC layer, an FC layer, and cloud computing. So the four key components of edge-centric IoT architecture are the cloud, IoT terminal, edge, and users. The architecture design takes into account both the available resources and each party distinct qualities. Users utilize the intelligent IoT to make their life easier, and they commonly connect with the Internet of Things and devices via cloud or edge-based interactive interfaces rather than directly with IoT peripheral. The Internet of Things and devices is deeply embedded in the physical environment. They feel and act to manage the physical environment, yet they aren't challenging when it comes to hard math. Despite the fact that cloud resources are virtually limitless, they are usually physically segregated from peripheral devices. As a result, a cloud-based IoT system is unlikely to deliver adequate performance, especially when real-time data is required. As the system central component, the edge may be able to assist the other three parties in collaborative and complementing cloud and IoT peripheral for improved performance. So this is nothing but the edge computing, wherein IoT users make queries to access IoT data or order to change the Internet of Things devices in an edge-centric IoT architecture. So next, in the edge computing, in the computing models of IoT, we are having middleware. And the diagram that shows in front of you is the result of one of the study, uh, wherein the function of middleware has been compared or classified on the architecture based, and the benefits of the architecture has been provided. So if we take the component-based approach over here, then benefits are reusability, abstraction supported independency. So here it is clearly, or it is obvious that if we are taking the component-based approach, then independency will be there because the various components do their or perform their functions. Then abstraction support will be there because if components are there, then definitely we can maintain the security as well as the level of abstraction wherein we can control our how many information or how much information to exchange to other components. And definitely the component based approach is also in terms of reusability, wherein if components are there, then we can use those components again in future or in other application. So the second architecture for middleware is the distributed, where the resource sharing is possible. And as it is distributed, then this is open. And as it is distributed, then definitely we can scale it as per our requirement in future. The concurrency is also achieved in the distributed system because we can perform the same. We can respond to multiple queries, or we can perform the same task on various machines. Then fault tolerance also can be done because the distributed system is there. So if anything goes wrong for one server, then definitely the other servers are available and can maintain the middleware functions over there. Then service-based approach is more towards the providing service. The service is classified and it can be reused and also scalable, because if we are going the architecture that the particular service is provided, then we can scale that service because it's having its own functions. Then the benefits is also the availability and platform independence is also there, because definitely if the service based architecture is there, then we can have independence domain implementation over there. If node-based architecture is there, then the availability and mobility both are there. As we just mentioned the example of train, where the mobility is there, we applied the fog node inside the train. If centralized architecture is there, then we are having simplicity, security, as well as the manageability. Uh, because simplicity in the sense the control is given to a single entity, and it's simple to have request response functions. And then security is also there because it is centralized to one server or to one location, so it can be managed only there, and it can be managed easily because it is centralized. So if it is centralized, then definitely the management of centralized things is easy. And if the architecture is client server, then the function of middleware is server separation, because a server is separated, and uh, the function of the server is already defined. Then resource accessibility, security, backup, and recovery, everything can be done in the client server architecture. So this is the middleware computing model where the benefits of the various architecture means architecture based benefits has been uh, shown over here. I will cover the blockchain in next slides. Um, so till this point, we have gone through the architecture as well as the ecosystem of the IoT. Now, we are looking into the emerging trends of IoT. So the first emerging trend is the edge computing. So this is the architecture diagram of the edge computing. So if we see what is edge computing, so the edge computing has been used in the IoT for reducing the latency and improving the data processing. So edge computing is a transformative trends in the Internet of Things actually, and bringing computation and data storage closer to the device that generate and utilize the data. This localized approach minimizes the distance data must travel to be processed, significantly reducing the latency and improving overall data processing efficiency. By enabling data processing at the edge of the network, IoT devices can respond more rapidly and operate more reliably, which is critical for time-sensitive application. So edge computing in IoT is one of the biggest achievement of technological advancement in our time, as IoT can be potentially address some of the most pressing challenges of our time, including food and water scarcity, climate change, and global health crisis. The integration of edge computing amplifies its impact manifold. Edge computing significantly reduces latency by enabling instantaneous data processing from sensors and cameras, which is essential for real-time decision making in safe navigation and collision avoidance. So in manufacturing, reduced latency allow machines to quickly respond to control command and adjust, enhancing productivity and precision. Wearable device and medical sensors can analyze vital sign on site, providing immediate feedback to healthcare providers and patients. crucial in emergency situation. By processing data locally, edge computing optimize bandwidth usage by transmitting only essential information to centralized cloud servers, reducing data volume and transfer cost. Edge devices can aggregate and perform initial data analysis, transmitting only aggregated or summary data to the cloud. Further, minimizing network data transmission. Local data processing with edge computing enhances privacy and security by keeping sensitive information close to its source, thus reducing the risk of data breaches during transmission. Organization gain improved data control by processing data on edge devices, implementing robust security measures tailored to specific local requirement and reducing dependency on third-party cloud services. Application of edge computing are widespread in industrial IoT. Edge computing enables real-time monitoring of manufacturing processes and machinery. Sensors collect data on equipment performance processed locally to detect anomalies and optimize operations. Predictive maintenance benefits from real-time data analysis, predictive equipment failure before they occur, reducing downtime, extending machine lifespan, and saving costs from unplanned repairs. Quality control improves as edge computing allows immediate inspection and quality assurance on the production line, identifying and removing defective products promptly to ensure higher product quality and reduce waste. In healthcare also, edge computing supports immediate data analysis from wearable devices and medical sensors, generating vital health data such as heart rate, glucose level, and blood pressure, providing timely insight and alerts to healthcare providers and patients. Remote patient monitoring is enhanced by continuous local data analysis, detecting critical health changes for rapid intervention and improving patient outcomes. In hospital, edge computing is streamlining operations by managing and analyzing data from various medical devices and systems, improving resource allocation, patient management, and overall healthcare delivery. In cities also, edge computing optimizes traffic management by processing data from traffic camera sensors and connected vehicle in real time, reduction congestion, improving road safety, and enhance public transport efficiency. So public safety is uh, taken under consideration as surveillance cameras and environmental sensors use edge computing to detect and respond to incidents, fires, and air quality issues, enabling faster emergency response and better disaster management. So these are the few of the benefits of edge computing over the other peer computing models. The second trend of IoT is 5G, enhancing connectivity and network capabilities. So actually, the integration of 5G technology is set to revolutionize the Internet of Things by providing enhanced connectivity and network capabilities. Actually, 5G offers significant higher speed, lower latency, and the ability to connect a massive number of devices simultaneously. This makes it a critical enabler for next generation of IoT applications, supporting a wide array of industries and transforming how we interact with the technology. And actually, key feature of the 5G in IoT includes high speed and capacity, ultra low latency, and network slicing, all of which significantly enhance the performance and functionality of IoT devices and applications. 5G network can support high data throughput, essential for IoT devices generating large amount of data, such as high definition video surveillance cameras, industrial sensors, and connected vehicles. This ensures seamless data transmission without congestion and provides consumer with faster download and upload speed for smoother streaming. real-time gaming, and rapid access to cloud-based applications. The ultra-low latency of 5G is crucial for time-sensitive applications requiring instantaneous response times. Let's take an example. Remote surgery can be performed with minimal delay, ensuring precision and safety. So this is also one of the uh, advantage of 5G technology, 5G integration in IoT. Autonomous vehicle benefits from real-time data from sensor and other vehicles, enabling split-second decision-making and reducing accident risk. And in the industry of automation also, 5G allows manufacturing process to be controlled with high precision, enabling real-time adjustment and coordination between robotic system, enhancing productivity and safety. Network slicing in 5G enables the creation of multiple virtual networks within a single physical 5G network. Each slice can be tailored to specific requirements such as bandwidth, latency, and security, ensuring optimal performance for diverse IoT applications. This capability supports various use cases simultaneously, from critical applications like healthcare and emergency services to high bandwidth entertainment services, all on the same network infrastructures. So application of 5G in IoT includes smart cities, healthcare, and agriculture. So these are the trends of IoT, actually what I would say. In smart city also 5G enhanced traffic management through real-time communication between traffic lights, vehicle and traffic management centers, facilitating dynamic traffic control, reducing congestion and improving traffic flow. Connected vehicles receive real-time updates about road condition and alternative routes. So we all know that 5G is having too many benefits, and it is the most, what I would say, promising trend in terms of IoT future. Apart from it, in healthcare also 5G high-speed, low latency capabilities enables high-quality video consultation between patients and doctors or healthcare providers, making healthcare more accessible, especially in remote areas. Wearable devices and home health monitors can continuously track patients' vital signs and transmit data in real time to healthcare providers, allowing early detection of health issues and timely intervention, improving patient outcomes and reducing hospital readmissions. Mobile health uh, units equipped with 5G connectivity offer advanced medical services on the go, connecting patients with specialists who can provide remote diagnostics and treatment plan. In agriculture also, 5G enables precision farming through IoT sensors that monitor the condition of the soil and the health of the crop and the weather pattern in real time. This data is used to optimize planting schedule, irrigation, and pesticide application, leading to higher yield and more sustainable farming practices. Automated irrigation systems connected with 5G can adjust water usage based on the real-time soil moisture data and weather forecast, ensuring optimal water use and reducing waste. Livestock management is improved as the farmer can monitor the health and location of the livestock through wearable sensors, receiving real-time alerts to potential health issues, improving breeding programs, and optimizing feeding schedules. So these are the few of the uh, uh, trends going in favor of the 5G, where the IoT advantage has been taken in various fields like healthcare, as well as the uh, farming field, automobile field, etc. Then the another trending area for the IoT is just blockchain technology. It is also increasingly recognized for its potential to secure IoT transactions and ensure data integrity. By providing decentralized and tamper-proof ledger, blockchain can address many of the security and privacy challenges associated with IoT. Uh, so, the blockchain decentralized architecture distribute data across multiple nodes, making it highly resistant to tampering and cyber attacks, since altering a single node does not compromise the entire system. The immutable nature of blockchain ensures that once a transaction is recorded, it cannot be altered or rollback, protecting against unauthorized changes and fraudulent activities, thus ensuring data remains secure and trustworthy. Advanced cryptographic technique further enhance securing by encrypting each transaction and linking it to the previous one, creating a secure chain that is difficult to hack. Data integrity is reinforced through blockchains, transparent ledgers, which records every transaction in a way that is accessible to all authorized parties. This transparency allows stakeholders to verify the authenticity of the data, fostering greater trust in the system. The tamper-proof nature of the blockchain ensures the recorded data cannot be altered, which is crucial for maintaining the integrity of the data collected and processed by IoT devices. Additionally, blockchain provides complete traceability of all transactions, which is particularly important in supply chain management for tracking the origin and journey of the product, ensuring their authenticity. Blockchain also enhances trust and transparency by providing verifiable records of transaction and interaction, which is beneficial in scenario where multiple parties need to share the trust data. Smart contracts, which are self-executing contracts with the term of agreement directly written into the code, facilitate automated transaction when predefined conditions are met, reducing the need for intermediate or mediator and enhancing trust. In IoT ecosystem where devices often interact autonomously, blockchain provides a decentralized trust mechanism, allowing devices to independently verify the authenticity of data and transaction without relying on a central authority. So this is again what I would say. This is again the fog computing advantage that has been mentioned just now. Application of blockchain in IoT span various industries. In supply chain management, blockchain can track the journey of products from the manufacturer to the consumer, ensuring their authenticity and preventing counterfeiting. Each step of supply chain can be recorded on the blockchain, providing a transparent and tamper-proof history. This enhances traceability of recording every transaction and movement of goods, helping to identify inefficiency, reduce delays, and improve overall supply chain management. Smart contracts enable automated and secure transaction between IoT devices, such as automatically executing a transaction to pay for energy consumption based on real-time data from smart meters in a smart home. This increases efficiency and reduce cost by automating transaction and reducing the need of mediator. In energy management, blockchain facilitates the management of decentralized energy grids by recording energy transaction between producer and consumer, ensuring accurate tracking of energy production and consumption and enabling more efficient energy distribution. Peer-to-peer energy trading is also enabled by blockchain, allowing individuals to buy and sell energy directly from each other, promoting the use of renewable energy sources and reducing reliance on decentralized energy providers. In healthcare, blockchain ensures the secure exchange of health data between patient, doctors, and hospitals, and insurers also. Patients can control their data, granting access to trusted parties while maintaining privacy. Blockchain can also track the journey of medical supplies from manufacturers to healthcare facilities, ensuring the authenticity and integrity of medicines and medical devices. So these are the emerging trends, blockchain technology, and it is having, what I would say, it is having application in various fields. Again, like in ledgers, as well as maintaining the portfolios, and also the maintaining the healthcare data, etc. And the last emerging trend as of now is artificial intelligence or IoT. So artificial intelligence is the future of IoT, enabling a smarter and more autonomous system through machine learning and data analytics. AI can analyze vast amount of data generated by IoT devices, uncovering patterns and insights that drive intelligent decision making. This integration enhances the capabilities of IoT, making system more efficient, adaptive, and responsive to changing conditions. Key contribution of AI to IoT encompass data analytics, automation, and enhanced decision making, which together significantly enhance the functionality and efficiency of IoT systems. AI algorithm can identify pattern and correlation in massive datasets generated by IoT devices, such as analyzing usage pattern in smart homes to optimize energy consumption and enhance security protocols. Machine learning models can forecast future events based on the historical data, predicting equivalent values in industrial setting before they occur. Enable primitive maintenance and minimizing downtime. AI also processes the analyzed data in real time, providing immediate insights and enabling quick responses to changing conditions, which is crucial in application like autonomous driving, where timely decision making is essential. AI also enables the automation of complex and repetitive tasks, reducing the need for human intervention and increasing the operational efficiency. In agriculture, AI-powered drone autonomous monitor crop health and apply fertilizers or pesticides as needed. AI allows IoT system to adapt to a new information and changing environment, such as adjusting heating, ventilation, and air conditioning system in a smart building based on occupancy patterns and weather forecast to optimize comfort and energy use. RPA, like AI-driven robotic process automation, can automate administrative and logistical processes such as inventory management and order processing, enhancing efficiency and accuracy in various industries. Robotic process automation can also be used in configuring the mundane task or day-to-day task or monotonous task that facilitate or the process of monotonous process to get automated. AI-driven insights help organization makes more informed decision. Like AI can analyze consumer behavior data from IoT devices to personalize marketing strategies and improve customer engagement. AI can provide insight into product performance and customer feedback, guiding the development of better products and services. In manufacturing, AI analyze data from production lines to identify area for improvement and innovation. AI can assess and mitigate risk by analyzing data or potential threats, such as monitoring transactions for fraudulent activities in finance or predicting and preventing potential health risks based on the patient data in healthcare. Applications of AI and IoT span various domains, including smart homes, healthcare, and IoT. In smart homes, AI-powered virtual domain, including smart home, healthcare, and industrial IoT. In smart homes, AI-powered virtual assistants like Amazon Alexa, Google Assistant, and Apple Siri provide a wide range of services, from controlling smart home devices to offer personalized experience based on the learned user preferences. AI also help IT professionals to perform their day-to-day activities like performing coding, finding the solution, writing emails, using different AI-based available tools like ChatGPT and also Google Gemini. AI controlling smart home devices to offering personalized experience based on the learned user preferences. AI controlling smart home devices to offering personalized experiences based on learned user preferences. AI enhance home automation system by enabling seamless control of lighting, heating, and security and entertainment systems. Adjusting setting based on user behavior to optimize comfort and energy efficiencies. AI analyze energy consumption patterns and suggest way to reduce usage, such as scheduling appliances to run during peak hours or adjusting thermostat based on the weather forecast. In healthcare, also AI can analyze data from IoT health monitor, electronic health records, and public health database to predict and track disease outbreaks, allowing for early intervention and better resource allocation. AI analyze patient data to develop personalized treatment plans, identifying the most effective treatment based on individual patient profiles and his or her historical data. AI-powered IoT devices continuously monitor patients' vital signs and health metrics, providing real-time data to healthcare provider, enabling proactive management of chronic disease and timely intervention in emergencies. In industrial IoT, AI predict equipment failure by analyzing data from sensor and historical maintenance records, allowing for timely maintenance, reducing downtime and extending machinery lifespan. AI optimize manufacturing processes by analyzing production data to identify inefficiency and area for improvement, leading to higher productivity, reduced waste, and improved product quality. AI enhances supply chain operations by predicting demand, optimize inventory level, and improving logistic ensures products are available when where they are needed, reducing cost and improving customer satisfaction. So these are the four, what I would say, trends in the field of IoT. And these are the actual the research opportunities as of now, as far as the IoT is concerned, because we have seen the architecture of IoT, and so this is based on the various layers, what I would say, perception, networking, middleware or processing, and application layer. So the first layer is the perception layer, which uses sensor to collect data. Sensors such as movement, camera, light, global positioning sensor, temperature sensor, and other utilized in IoT devices. So we can take the advantage of existing sensors and apply or implement these sensors in various domains based on their nature. The actuator is a device that converts electrical energy into different form of energy to change the environment. Speakers, motors, heating element, and cooling components are example of actuators. So actuator comes in three different categories depending on the operation: electrical, hydraulic, and pneumatic. So based on these various actuators, we can also implement them as per their nature in the various domains. A smart home system is the most excellent example of using sensor and actuators. Many sensors and actuators are used in home to lock and unlock doors, turn on and off lights, turn on and off other electrical appliances, and control the alert system, thermostat, and digital fingers. Research can work in this approach to improve the accuracy of real-time data detection with sensors. Another consideration at this layer is the preservation of the privacy. So based on this various components available at various level of the IoT, we can take the advantage of the research. So that's it from my end. And these are the references that I have used to prepare this presentation.
Thank you, sir. Harshita, madam. Any question from participant?
Yes, sir.
Yes, Harshita, ma'am, over to you.
Over to Arshita, ma'am.
Okay, sure, sir. Um, Thank you so much, sir. I sincerely thank you, Mr. Vishal Joshi, sir, and Dr. Gaurinath Banda, sir, for this wonderful presentation. Your insights have given us a clear understanding of the subject and inspired us to think about the future possibilities in this field. We truly appreciate the time and the effort you have put into the sharing your knowledge with us. Thank you so much, sir, once again.
Thank you, madam.
Now I would like to inform you all that tomorrow also we will be taking this session at 6 o'clock, and we are done for today, sir. Thank you.
Thank you, sir.
Thank you, sir. Thank you, all the participants.
सर एंड कर दो मीटिंग.
Yes, sir. Yes, sir.
एंड कर रहा हूँ सर मीटिंग.
Sir, participants are leaving. Sir, still some participants are demanding feedback link in chat box.
सर व्हाट्सएप पे डाल देते हैं उनके.
Okay, sir. We will share in WhatsApp.
Okay, share in a WhatsApp group, no problem.
सर मैं